Welcome back, and by popular demand, nerds. Nerds. There you go. Okay, we go. Let's do it. What? Yeah, I already tested it. This video works just fine. We are ready to continue this set of questions where we were yesterday, and we were trying to talk about the end behavior of graphs just by looking at the polynomial, and then we were supposed to find their extreme values and their zeros. This one, I forgot to write down that it goes through x equals 0. But I did mention that it doesn't have any extreme values, but it's only 0 as x equals 0, which we saw on the graph. Okay, this one, we're going to talk about what its end behavior is based on its degree and the number in front. So this one has a degree of 4, so this is an even degree polynomial. When the degree of the polynomial is even, what does that tell me about my ends? Anybody know? Same direction. Okay, so they're going to point in the same direction. So they're either going to be both up or both down, one of the two. But my leading coefficient is negative. So since I have a negative on the front, what'd you say in the back? Down. Yep. So since the front number is negative with an even degree, I got both, let's try that again. Both endings pointing down. There we go. So what we can do is we can, what we can do is we can sketch the endings. So both down. We got a left down and we have a right down. There we go. Let's use our limit notation to describe those two downwards arrows. This one's going down and to the left. So the limit as x goes to, well, the left side of the number line. What's on the far left? What am I heading towards? Negative infinity. Good. My y values, well, I said it's pointing down, so if they're going down, what are they heading towards? Also negative infinity. There we go. Let's do the other one. This one's heading towards the right. So if going to the left was negative infinity, going to the right is positive. But it's also going down, so what's the y value heading towards? Negative. Paul, you got a question for me?
Is that LIM?
LIM, yes, limit. LIM. Yes, absolutely. This is called limit notation. You have to have that structure. It's a pretty big deal in calculus, so that's why we're introducing it now so you get used to it. Let's actually graph it. That way we can find its extreme values and its zeros. So go to graphing calculator and y equals negative x to the fourth minus x. I'm just going to hit zoom 6 just to see what it looks like. Oh, okay. I mean, I know what it looks like. She says it's a cute little graph. I know what it looks like close to x equals 0, but I'm going to go ahead and zoom in. That way we can see its behavior a little bit better, if that's cool with you. So you can hit zoom, and then zoom in is option 2. And I'm just curious what's going on around the origin. So I'm just going to hit enter right there at 0, 0 again. Oh, I don't know if you guys caught it, if you saw it when it was happening, but it gave us a little wiggle right there close to the origin. Because of that, I'm going to hyper exaggerate the shape when I draw it. You guys okay with that? Yes? You're okay with that? All right. Well, maybe it wasn't too much of a wiggle. Gave us a little shake and bake, you know what I mean? Yep. I don't know if you know this, but you can see that it goes to the x-axis at -1 and at 0. Why is it what? What's your calculator? Okay, all right, I'm going to pause the video while I fix your calculator again. Yeah. So syntax errors adjusted, people's, hey, whoa, hey, okay. All right, I'm going to go ahead and draw this thing. It looked something like this. So it had this like weird bump in it right there. I tried to exaggerate it to show you that it did something like that. I don't know. You can see it's not a parabola. It's some kind of funky deal, you know. We know it's zeros. They're at 0 and -1. But this graph does have an extreme value. It has a maximum right there. And we're going to find the coordinates of that maximum using second trace maximum. Second trace, and maximum is option 4, so I can just hit 4. And then it wants me to do the whole left bound, right bound stuff. So I'm going to go to the left of the top of the bump, hit enter. I'm going to go to the right of the top of the bump, hit enter, and then I'm going to go in between the two lines it drew and hit enter one last time. And I will see my maximum is at the coordinates -0.6, actually 0.63. That is 3 decimals. And then the y value is 0.472. There. So this is how you're going to find maximums and minimums. Second trace maximum, second trace minimum. Are you guys comfortable with that? Awesome. What's up? Yes, we have. But we did it for quadratics. We've never done it for polynomials. We did it for cubics, kinda, yesterday, I think. But this is in behavior and extrema. Cool. What if I just wanted you to be able to find the zeros? What about that? Well, I'm going to be real with you. This thing factors. So we could just solve by factoring. I'm going to assume you know how to factor because this is AP. So I'm going to write this in factored form. It's x and then x minus plus 2, x minus 3. This is what it factors to. So we can see its answers are x equals 0, x equals -2, and x equals +3. But what if it wasn't one you could solve by factoring? So yes, it's a really obvious question, but that's because I wanted you to know that we could do it through factoring, but we can't always do it through factoring. So if we can't do it through factoring, what do? We graph it on our graphing calculator, and we ask our calculator to tell us where it intersects the x-axis. So I'm going to go back to the calculator, and I'm going to cover up the factorization because we're going to pretend we couldn't see it. And we're going to type it again. X to the third minus x squared minus 6x. This one didn't ask me to find the extrema, so I actually don't care if they land on the standard graph screen. Oh, that's right, I zoomed in. Oops. So I'm going to have to hit zoom 6. You see why you always hit zoom 6? So you don't have to wait for it to stop graphing? I should have just done what I always do and hit zoom 6. But I forgot to. Anyway, there it is. Again, it has pretty solutions. We can see them. What I'm getting at is, what if they weren't pretty? What if we couldn't find them by factoring? What would you do? Well, you could go, I'm not going to do it, but I am going to show you. Second trace 0 is something you could do. But if you do second trace 0, it's going to make you do left, right, guess of the answer. Bless you. And I find it faster, and this is just a me thing, I find it faster to say, well, if it's touching the x-axis, y is 0. So I like to just graph a secondary equation and do second trace intersect. It just ends up being faster for me. Yes? What's going on? Is that a hand up or no? Oh, okay. I just think it's faster to do second trace intersect. Second trace 5, enter, scroll, and then hit enter again. Oh, look, x equals -2, just like we knew it would. But my point is, that's how you would do it. Because then you could go second trace 5, enter, scroll, enter. Oh, look, there's the second one. Second trace 5, enter, scroll, and get the third one. And I'm telling you, it's much faster to do what I just did than to do left, right, guess 3 different times. Yes, Charlie? So because your calculator has the ability to, oh crap, I have to bring that back. Dagnabbit. Well, there is no undo feature. I wish these calculators had an undo feature. That would be really beneficial. So the reason why it's asking for second curve or in third curve and all that crap is because there's nothing that stops me from having other things. on the screen. So if I had multiple graphs going on, there's 2, and then there's the third one. Oh, figures. What a boring graph. Well, anyway, now if I go to second trace 5, it says, is this the first curve? And having a color calculator helps because you can see the directions are in blue, so it's talking about my blue curve. And I could say, yeah, that one. And it says, what about this red one? Was this red one the second one? I could say, I could not hit enter. And instead I could hit down or up. All right, down, up took me to the blue curve. And I go, no, I want the black one, down, down. I can say that's the second curve. And they go, fine, take a guess. And then go, it looks like right there. And then it says, yeah, they intersect right there. So I could have multiple curves on there, and I could just hit up and down for the second one. That's why. I'm kind of cheesing it by using the x-axis as a quote-unquote curve. Because second trace intersect is just faster than second trace zeros. But that's why. And if it's the only 2 things you have on the screen, it's literally second trace enter scroll. Or second trace enter scroll. And it just becomes muscle memory. And if you always have the x-axis as the second one, you're always just scrolling left or right along the horizontal line. It just ends up being fast. So it's just out of habit. So we use technology to get our 3 answers. Of course, we knew them to be -2, 0, 3. But second trace intersect is your friend. Unless you're, Ashley, does your calculator find zeros as easily as it finds maximums and minimums? That's cool. Shut up. All right, so anyway. Just to be clear, Casio calculators are great calculators. I just don't know how to use them, and they're for engineers, not for mathematicians. Why? I don't know. Oh, these could have games. You can install games. I saw Mr. Lash playing Pac-Man on a calculator yesterday. Yeah, Tetris, Pac-Man, Space Invader, puzzle packs. No, they're apps. Look, you see where it says apps? You just hit apps, and they'll be in your apps menu. Or no, programs. They're programs. You go to program. Right now, mine has no programs in it, but you can download games and put them in your program menu. You go to the internet. Yeah. Jailbreak? How do you do that? Oh, okay, so I'm going to be real. The Mr. Lash was playing Pac-Man on Mr. Case's calculator. Okay, so. Nah, you guys call it jailbreaking. It literally just means allowing third-party programs. That's all it means. Nah, it's not scary. All right. Here's a concept that you should have learned in Algebra 2 Honors. No, you had better have learned it in Algebra 2 Honors. It's called multiplicity. Yes, you all did. Right here, this equation, we saw its graph, right? Well, let me put it back on the screen since I can't use Desmos on the camera. Y equals, I cleared it again. I hate everything. Oh my God. What was it? X times X plus 2 times X minus 3. I just typed it in factored. Whatever. It doesn't matter. The factorization of a polynomial shows you what we call the roots of the polynomial. So when it's factored, the pieces, the factors, are called its roots. You don't have to know that vocabulary yet. I'm just letting you know. What you do need to be able to do is identify the power of the roots. And all 3 of these have a power of 1. What kind of equations have a power of 1? Linear, which stands for line, okay? Any root that has a power of 1 will interact with the x-axis like a line would have. It will cross right through the x-axis as if it were a line, because it's power 1. Power 2 are quadratic, right? And quadratics are shaped like U-shaped graphs. So if I went back to my y equals menu and I insert a power of 2 right here, Now, when my graph interacts with the x-axis at -2, it will look like a quadratic at x equals -2. I just said you should have learned it last year. Yes. So if you look at how the graph is behaving at x equals -2, you can see that it looks like a quadratic at that x value now. And for funsies, if I change it from a 2 to a 3, cubics are third power, and I hit graph. At x equals -2, it is now behaving like a cubic. This is called the multiplicity of the root. It tells you how the graph interacts with the x-axis at its 0, x-intercept. 0 is another word for it. We call it the multiplicity. Here, because that graph looks like an x to the third graph, that tells me at this solution, the root would have had a power of 3 on it. Because at this solution, which is just x equals 0, so you just write it x would just be its root. Because it behaves like a straight line and goes through, just directly through without getting fancy, then this root, x, has a power of 1. And because this last one behaved like a quadratic at its solution, its root would have had a quadratic power on it. We basically say odd multiplicities cross through the x-axis, but then you have to talk about, well, how did it cross through? Did it cross through straightwise, or did it cross through curvy like a cubic? And then we say even multiplicities bounce, quote unquote, bounce off the x-axis. Mr. M, is it going to be above the x-axis or below the x-axis? Ah, fantastic question. The answer is you need more information. Basically, you need to know what the endings are doing as well. So we have to know how the end behavior is going to work to know if we're going to have bounces above or below. And are my crosses going to have a positive average rate of change or a negative average rate of change? Well, again, it depends on the zeros and the end behavior. You need both pieces of information. By the way, the two endings of this graph point the same direction. What does it tell you about the degree? Even. And since they both point down, what do we know about the leading coefficient? Negative. Good. Just putting that in your mind. Oh, and if you were really curious, power of 3, power of 1, power of 2, that adds up to 6. This would be a negative 6th degree polynomial, if you were interested. But Mr. M, it just says odd. How do I know that it's a 3 and it's not a 5? Well, you don't know it. Actually, it could have been a 5. How would you identify it? Well, you would either have to see the equation, or do you remember yesterday when I was showing your quadratics and your 4th powers and your 6th powers and stuff, and I showed you that as the exponent went up, the graph flattened out close to its vertex? The same thing happens for cubics, 5th powers, 7th powers, 9th powers. They will flatten out even more around their inflection point. But if we're not told what kind of degree we're looking at, we will just assume things that look cubic are cubic and things that look quadratic are quadratic, parabolic, okay? It's called a polynomial of minimum degree. That means don't make it bigger than you need to. I had a student the very first year I taught Algebra 2, Nathan Kozlowski was his name. And this was like, 9 years ago now. He was like, but I can use any odd number I want, right? And I was like, yeah. And he's like, and I can use any even number I want, right? And I said, yeah. So for my tests, which used to be paper-based, he would write his polynomials, and for his odd powers, he would put 69, and for his even powers, he would put 420. That's good that you don't get it. That everybody who's watching this video, that would be Isabella Lessa, who doesn't get the joke. If you want to roast her. Anyway, don't tell her, this is school. Okay. Anyway. And I remember that kid's name because that was ridiculous. Also, he wanted to hug me all year and I wouldn't let him. I had to tell him, don't touch me, Nathan. You know, try to hug me. Don't do it. It will be on YouTube, but is he watching my videos? I doubt it. He graduated a long, long, long time ago. I'm sure he remembers me. Does he care is the question. All right, now, what we're going to do is we are going to sketch this graph. We're going to sketch it using end behavior and multiplicities. Question for me, Mark, or no?
I have something to say.
He has something to say. Can I?
A little up.
Yes?
Graph.
Yes.
It's the third, the first, and the second.
Yes.
And if you add those up, it goes to the sixth.
Correct. That's how I know it's a sixth degree polynomial, because I added those exponents.
Do that for like the one at the bottom to get fit.
Exactly. So what Mark just realized is that what I did was I added the exponents. So yeah, this would be a fifth power. This is a fifth degree polynomial. Now I'm not going to give you one like this, but what if is, students sometimes say a what if, and they'll go, what if it said this? Let's just say I made it up like that. What's the degree of that polynomial? That's a fifth degree polynomial. Reason why is because if you squared this set of parentheses, you would get an x to the fourth, and then if you multiplied it to this, you'd get an x. So like, what is this degree of the polynomial? It's a seventh degree polynomial, because if you FOIL this out, you got x squared times x squared times x squared, which is x to the sixth, x to the seventh. So we can't always just add the exponents, but we can add the, if there's no powers in my roots, then yeah, I can just add the roots exponents to see the degree. But I would rather you think, instead of trying to look for that shortcut, I would rather you think, if I multiplied all this out, what would I get? If I multiplied all this out, what would my first term be? If I went through all the distributions, what would the very first term be? X to the fifth. So let's talk about that. First and foremost, the degree of this polynomial is 5. We see that. But the leading coefficient, well, what is my leading coefficient? It's 1. That's positive. So because I have a fifth degree polynomial, what do I know about my endings? Same direction or opposite directions? Opposite directions. And because it's positive on the front, am I going to have an average rate of change that's positive or negative? Positive. My endings will do this. Left down, right up. We now know what the edges of this graph look like based on the leading term. Cool with that idea? Great. Now we can look at what our zeros are. It's what makes the inside equal 0. So x equals -2 and x equals 1. At x equals -2, because of this multiplicity of 3, what will my graph behave like? It'll look cubic. At x equals 1, because the multiplicity is 2, what will this behave like? Quadratic. It's going to look like a parabola. We know what our endings look like, and we know how the graph is going to behave at every one of its zeros. We are ready to rock and roll. I am not going to put any y values on the y-axis. How come? Because I don't care. That's why. They're not important. We're just trying to get a general idea of what this graph would look like. I know it's going to interact with the x-axis at -2 and at +1. I also know what the endings will look like. I've got going left, going down, and I've got going right, going up. See how I put those at my furthest left and furthest right solutions, at my zeros? There you go. Now all we have to do is figure out what the spaghetti is going to look like. Okay, well, at -2, we said it would look cubic. So it's going to have to do this. Doesn't have a choice. There will be an inflection point at x equals -2. And at 1, we said it looks parabolic. Means it bounces off the x-axis, so it does this. All we have to do is connect those two things. No, it's a sketch. So what we know is we have an inflection point at -2, and there's a maximum here somewhere. So we would have to find this maximum if I ever asked you what the maximums were, and if you had to estimate its inflection point, you'd go between these two, because there is another inflection point somewhere in here. There's also another one somewhere in here, but that's it. That's all you have to be able to do. It's not bad, right? And it's not new. You did this stuff last year. Who? Okay, hold on. I'm pressing pause so we don't call out anybody. Anyway. Look at this piece of spaghetti. You see this thing? We are going to write a potential equation for it. And the way, yeah, that's what we're going to do. And by the way, you have a test question that looks just like this. Oh, also, you have test questions that are like this, where it says, like, find the zeros. That's part of your free response. So if you can find zeros and you can find maximums and minimums using your calculator, you can do part of the free response stuff with the graphing calculator already. So that's good news on that stuff. Okay, what we're going to do is we're going to set up the roots first. Let's write out the roots that we're going to get. Because this graph interacts with the x-axis at -4, we know we have a root that says x plus 4. But based on the way it's behaving there, what power would we say that this root has? Cubic power, so third power. Here, because the graph is interacting with the x-axis at x equals 0, my root is x, but its exponent is 2 because it's behaving like a parabola. Well, no, don't say -x squared, because we don't know if it's a negative number on the front of the whole polynomial or not. So what we know is that the graph is behaving like a quadratic, so it has a quadratic power. Don't worry about up and down. The up and down will be determined by the end behavior. Okay? The roots themselves, we'll just let them be how they are. I don't know. I would only write what I'm writing. This one is going to be x minus 2, but what is its power based on its behavior? 1, because it looks like a line. And the last one's going to be x minus 4, first power, because it looks like a line. So I can write my potential polynomial in factored form. I'm not going to bother multiplying it out. And it really doesn't matter what order you write the roots. It's just that since this one's going to be a naked root, just x squared, typically we see those x's on the front, meaning it's not in parentheses. We typically see those on the front. So I got x squared, and then I'm going to go from left to right. X plus 4 cubed, and I already have x squared, x minus 2, x minus 4. At this point, based on the fact that my end behavior is different directions, what do we know about the degree of the polynomial? Not at the degree. Odd. And we can prove it. 2, 3, 4, 5. So this is a fifth. Excuse me. 2. No, I said that right. I'll be okay. Can I not add? What did I say? 2, 3 because it's a freaking 3? I was like something. I was really struggling with that. 2, 5, 6, 7. There we go. I did. I went 2, 3, 4, 5. Knew it was wrong and couldn't figure out why. Anyway, it's a 7th degree polynomial, so it's odd. But because it's left, up, right, down, is it positive or negative on the front? It's negative on the front. And the reason why we know it's negative on the front is because this thing has a negative overall rate of change. Now, hold on. Now, if you got lucky and got negative on the front because you said this was negative, but that's what you said. You said it was negative x squared. Don't call this negative x squared is what I'm saying. You said it, though. Okay, well, whatever. Yeah, sure. What time are we getting out of here today? Oh, wait, I have time to do the last question then. We're going to hop over this question and I'll explain how it works, but you already know. Look, it's the cardboard with us cutting the squares off to the sides, off the corners again. for the volume, just listen please. And you're going to find its volume equation. But rather than maximizing this volume, it specifically says the volume needs to be 484. So you graph a y2 as 484, and you do second trace intersect. Don't worry, I'll do it on Monday, but I'm not going to, I might even record it, but it won't even be part of these notes because you have that ability. You literally just set it equal to a number and do second trace intersect, which you've already done, I hope. If you had done the whole terrace, you know, the rectangle question, that was like, there was a garden that was a rectangle, and then there was a path that went around it from the other night. You were supposed to use second trace intersect for that. So you would have already done that work. Anyway, I have enough time in this video to get to this question here. And I fear that I might have misspoken a few days ago when I was talking about, and man, I hope I didn't record it because that makes me sound stupid. But I realized I said it wrong today. Here, I told you these two parabolas had a second difference of 2. And I said it wasn't a coincidence that the second difference was 2. It's not a coincidence that the second difference is 2. But because these are 2's didn't make these parabolic. Because these numbers were the same here or here, because they were the same number in the second rate of change, that's what made it parabolic. So when we use the first and second rates of change difference, if the first rate of change, which is slope, is constant, you know it's linear. If the second rate of change is constant, you know it's quadratic. If the third rate of change is constant, you know it's cubic, so on and so forth. I think I misspoke the other day and I specifically said if the second rate of change is all 3's, it's a cubic. I hope I didn't record that because it's wrong. I hope I didn't say that on a video. Anyway, to correct that mistake, here we have a table of values that come from a polynomial of some sort, and we don't know what kind. Our job is to figure out what the equation is using our calculator's regression features. So what we do is we look for our first differences, which is slopes, right? So we got first differences. From here to here is plus 0.2. And then from here to here I have plus 9.8. And then plus, and that's going to be plus 29. And at that, I'm just going to go, it'll go faster on a calculator. 99.7 minus 41.9. That's plus 57.8. Big numbers. And lastly, plus, again, it'll be faster on a calculator. 195.9 minus 99.7 is 96.2. Clearly, this is not linear. Oh, I do want to point out, I'm allowed to do the differences. Sorry, 96.2, I forgot the 6. I'm allowed to use the first, second, third differences, so on and so forth, because my x's are increasing at a constant rate. If these x's were like all over the place, we wouldn't be able to do what we're doing right now. They have to increase at a constant rate on the x's. So that was our first differences. Clearly not linear. These weren't the same. Now I'm going to go to my second differences. To go from 0.2 to 9.8, I'm adding 9.7. To go from 9.8 to 29, oh my gosh, I can't do basic math. 9.6, okay. This is going to be 19.2. 28.8. And the last one I'm not even going to try. 96.2 minus 57.8. That is 38.4. Okay, my second differences were not a constant values, therefore it is not quadratic. Go to third differences. 19.2 minus 9.6 is 9.6. And if you add 9.6, oh my goodness. Yes?
Should we do, you said for like third degree differences and so on, the x's have to be constant. Do they also have to be constant if we do second difference?
So whatever difference number gets you a constant rate of change, that is the type of polynomial. So this is a cubic, and you would use cubic regression on your calculator to get its equation, which is right below quadratic regression. Which after you put your data in, it'd be like stat, calc, cubic regression. Don't worry, we'll actually finish them. I just wanted you to have the ability to do your homework and make a good video. Grossiest nerds.